Welcome. In this lecture, we're going to go through what's called the second derivative test. So there are two different circumstances, and this is a test that's going to tell you about local minima and local maxima. And so the first thing is there's going to be a requirement. So first we're going to suppose, or requirement for, this is the second derivative test. Okay, so this is kind of like a pre-requirement, which is that we're only going to look at a circumstance where when we take the second derivative, it's going to be continuous near C. So continuous near some value x equals C. Okay, and then there are kind of two circumstances. So here's the first circumstance. So we'll do one circumstance here, and then we'll do another circumstance over here. Okay, so here's the first one, which is we're going to suppose, we're going to have two things. So suppose that we have, so the first thing that we're supposing is that when we take the derivative at our specific value C, so right, this is the derivative, and then we're going to plug in C, we're going to want that we're going to get 0. I'm going to say that's equal to 0. And so the second thing that we're going to require in order for this to work out is that the second derivative, so now we're taking the derivative one more time, right? And then, so make sure that you first take the derivative and then you plug in C. If you do it the opposite way, you always get 0, right? Okay, and then the second, because derivative of a constant is 0. Okay, so when we take the second derivative at C, that this is actually greater than 0. Okay, so if we're in the circumstance of both of these things being satisfied, then we know, so then we have that f has a local minimum at C, so f has a, so it has a local minimum at C, so he has a local minimum, and this is at C, so at that same value C that we plugged in after we took the first and second derivatives. Okay, and there's a picture which I think just makes this basically obvious, okay, which is that I'm looking at where my first derivative is 0, so I'm looking at where it's flat, right? So I'm looking here, but I'm concave up, right, because my second derivative is greater than 0. You can kind of see that this is a local minimum. And honestly, I wouldn't memorize the second derivative test. What I would do is memorize this picture, right? And know that, like, in this picture, this point here, right, my derivative has to be 0 there because it's flat. And it's, I'm concave up, but this looks like a local minimum. So I would just draw that picture, and then you can remember which of these things fits with which circumstance. Okay? Honestly, that's how I would remember it. So now let's look at the second circumstance. So suppose that I have that. Okay, so I have that. So the first thing, I still need that my first derivative is 0. Okay, so I still need that this is going to equal 0. Okay, so I'm getting a flat slope at that point. And the second thing that I need, though, now is I'm the opposite picture. I'm going to be concave down instead. Okay, so when this is less than 0 now, so if both of these things are true, okay, then we're going to have that f is going to have, well, let's draw the picture, right? I'm concave down. I'm looking at where it's flat, so I'm looking here, and you can tell this is a local maximum, okay? So then f has a local maximum at this value C, right? when x is equal to c, okay? And so this is where I have a local maximum. And from the picture, you can kind of tell. For some reason, if people don't draw the picture, they tend to swap these two things. So it's good to actually draw the picture so that you don't swap them and you get actually the correct circumstance. But you need both of these things to be true, and then you know you have a local maximum. You need both these things to be true, then you have a, local minimum. You need both these things to be true, and then you have a local maximum. And you also actually need these to be true before you can even look at these. Okay, so I hope that made some sense, and I'll see you in the next lecture.